Okay, I think this is time for me to begin with my presentation. Welcome, everybody, and thanks for joining my talk from zero to deep learning. My name is Fabio Tiriticco, and my Twitter handle is TicoFab, which is a lot easier to pronounce than my family name. And I have a word of caution here for you just before we start. This talk is going to be really an introduction from zero to deep learning. So if you're already you've already played around with AI, or you're already very acquainted with AI, then maybe this is not the place for you. We're going to have some code at the end, but not a lot. This is really starting from the basic, from the concept. So if you, on the other hand, are someone intrigued by AI, but maybe never had time to explore it in your time, this is the perfect place to start. With that said, there is also, of course, there is a Slack channel where you are more than invited to ask questions, or even ask questions in the chat as I speak. Also, I am based in Amsterdam, in Europe, so it's almost 10:30 at night here, and so if you see me falling asleep while I present, please notify someone in chat, and maybe they will wake me up. All right, let's get started. Who am I? I am a software engineer living in the Netherlands, originally from Italy, but living in the Netherlands for quite a few years, where I also work as a community manager. I founded and ran the Reactive Amsterdam meetup, where we talk about everything reactive, so reactive programming, RX Java, reactive systems, what you have it. And I also one of the organizers of the Kubernetes Community Days conference. Unfortunately, this year we had to cancel it because of the pandemic and also overlap with the virtual KubeCon. So my kudos and greatest respect goes to the organizers of this conference. Really, I am thankful and appreciative of all the effort that they put into organizing this event online. Now we get to the real talk. And every talk needs to have a great background, as you know. And so I'm going to start first by introducing the background that led me to do this, the project that became this talk. Once upon a time, it was still possible to work in offices. And in fact, about a year ago, I used to work for a client whose office was next to the Amsterdam airport. And now what you see on the screen is a section from Google Maps around the Amsterdam airport called Schiphol. And now the section that you see highlighted now on screen is the first airstrip that was built. It's like the original airport area. Now, as traffic grew over the years and there were more flights coming in, it was necessary to build a second strip. And that is the part that you see highlighted now that was built then. But as you can see, in the middle between those two, there was already that yellow road called A4. So they had to find a solution to make the two airstrips communicate efficiently. And so the best idea that they could come up with was simply to build a bridge over the existing highway. Now, the result is what I could see from my office is this view. The result is that every now and then you have these incredible planes, these huge, cargo, massive planes that are just strolling peacefully over this bridge, which is just meters, a few meters. What is it, like maybe 4 feet or 5 feet or something above these cars who look so tiny in comparison. And I don't know, maybe the image doesn't really show the awe that I had, but it was really incredible to see it from my window. Now, the one problem with this is that you'd never know when planes are going to pass by, and so here the idea for my side project. I would put a Raspberry Pi next to the window that takes pictures of the bridge at, say, any minute at some given interval, and I'm going to build from scratch and train a neural network. And this neural network needs to be able to tell me whether there is a plane on the bridge or not in that moment. And if there is a plane, I want to tweet it, because why not? So here's the setup that I created. You see in the left part of the image a picture of my Raspberry Pi at the window, overlooking on that bridge. There is in fact a plane on the bridge now in that picture, and on the right you will see two different pictures. The top one, in fact, has a plane on the bridge, and the bottom one has no plane on the bridge. All the Raspberry Pi needs to do is tell me whether there is a plane or not. I did create a Twitter account at the end of the project where I tweeted. It was called Planes on Bridge. There are, during the lifetime of this Raspberry Pi, I did about 1,100 tweets, and I had a grand total of 17 followers. So not maybe the most popular Twitter account ever out there, but it was fun. Actually, you could see the season changing and the trees, the leaves changing color. It was quite fun. All right, so let's say you know nothing, I know nothing about AI. How would we approach this idea? Well, we need to start with a deep learning overview. What is it actually? Deep learning is a subset of machine learning, which is a subset of artificial intelligence. And machine learning and deep learning really are ways to sort of train a computer, a machine, to make predictions about something. For instance, the two main common use cases for machine learning and deep learning are regression and classification, where regression answers our question, how much? And so, for instance, you see in the graph in the left part of the slide, maybe that graph correlates, I don't know, let's say house prices given their square meters or square feet. So the question would be, how much is this house going to cost me given the square meters of surface? And that is the regression use case is exactly finding this answer. The classification use case instead answers the question, what kind? So that image, maybe you remember, is from a few years ago. Someone trained a deep learning network to tell pictures of Chihuahua dogs from pictures of Raspberry Muffin. And, you know, I have trouble myself with some of the pictures telling which is what. So it's not an easy task. In general, classification cases is when we want to identify one object or more in our image. In our specific case of the plane is a classic classification cases where we have two possible classes of outcome. There is a plane on the bridge or there isn't. This is it. All right. In order to start building our own neural network without using, the cloud APIs of, Google Cloud or AWS or IBM, we want to build our own neural network. So where do we start? Obviously, we start from the basic. The basic of neural networks is, in fact, the artificial neuron, so-called after the neurons that we all have in our head, including animals. Let's say human animals, all animals have neurons in their brain. And the artificial neuron, when you try and describe it and look at it, it's basically a mathematical function. It's basically a mathematical function called transfer function that takes in a series of weight inputs. So in this case, W1, W2, all the way to Wn. The output of the transfer function is then put through another function called activation function. Now, this activation function, in reality, it will be just a filter. So imagine the activation function as a filter that decides whether the result of the transfer function is worth propagating further or not. So the outcome of the neuron as a whole will be either the outcome of the transfer function or zero. This is depending on what the activation function decides. This is it. That's it. This is the mythical artificial neuron. And you might wonder at this point, well, that doesn't look very, very powerful, does it? And you will be right. The power of neural networks is when a lot of different neurons come together. So what you are seeing now on screen is a typical example of so-called multi-layer neural network. Why multi-layer? Because if you read it from left to right, you will have some input values. For instance, they could be A, B, and C, right? Now, the input layer is consisting of neurons that receive these inputs, and these neurons are fully connected to the neurons in the first hidden layer. What they do, the neurons in the input layer, typically their transfer functions just let the value of the input pass through. So here we are, the input is passed on to all the neurons in the next hidden layer, in the first hidden layer. Now things start to be more interesting here because the neurons in the hidden layer may have different transfer functions and different activation functions. And so only some of them will eventually propagate something. Some of these neurons in this layer, their global output will be filtered by their activation function, and so it will be 0. So we'll have something like this. See, only 2 of those 4 neurons are propagating their information further to the neurons of the second hidden layer. Now, for the second hidden layer, exactly the same principle applies. So only some of them will propagate information further until we reach the output layer. The task of these neurons in the output layer is basically to collapse the information that they received from the previous layers and produce some output values. In this case, 2 and 5 made up. And if we change the input values, so we go back all the way to the left. So let's say that now our input values is going to be T, P, and G. We'll have that the input layer will propagate the input values just unfiltered through the first hidden layer. But then from here on, the configuration of neurons that propagate information might be different because the different transfer functions will react differently to different inputs. And so already from this very, very, very basic example network, you can appreciate how if we have more layers in the middle and a lot of neurons per layer, it becomes pretty much impossible for us humans to understand what's going on because the combinations are just infinite. Imagine hundreds of neurons in each layer and many, many layers. The combinations are just infinite or practically infinite for us. This is the main reason actually why these kinds of networks are called deep network. Simply because what goes on in the layers is hidden, is deep, is somehow non-transparent for us. This is also another reason why these kinds of network, they became very popular only recently, in like the dust, use cases really came to the surface in the last decade or so, because when there's many, many neurons and many, many layers, well, training these networks and doing the computational operations associated with them becomes really prohibitive. So only recently we had access to the computational power needed for this. All right, so this is a very basic example of our of a multi-layer neural network. Now the question is, how do we build a network starting from this example, a real network that fits our case? And here it comes my first revelation when I started looking at these things, that deep learning networks and the building of them is a bit of a trial and error stage. What do I mean? At this point in history, it's impossible to deterministically decide what network will be the best one for the task that we want to accomplish. We only know that for some problems, certain deep learning network architectures work better than others. So the next slide is going to show us, in fact, which are some kinds of problems and which are the architecture that best matches them. Convolutional neural networks are a specific deep learning network architecture that is absolutely super powerful for image recognition. So imagine human faces, animals, street signs, any kind of image. And the power of this network actually is mostly behind the hype and the success of AI in recent years. If you think about a product like a Tesla car, a self-driving car, it must be full to the brink of convolutional neural networks. That maybe there's, one network that's going to look at a traffic light and see what color it is. There's going to be one network that look at the horizontal signals, on the ground, the lanes. There's going to be another convolutional neural network looking at I don't know, maybe the indicator of the car in front, see if it's, flashing. Full of convolutional neural networks. Another architecture, recurrent neural networks. These networks are really, really complex. And their use cases are basically processes where inputs form sequences in time. So where the input that we receive at some given time has a meaning that is very correlated to the input that precedes it or that follows it. Think, for instance, about like a word in a sentence. When I say a word, that word has a meaning that is probably given by the entire context of the sentence. And so we need to sort of remember what came before. And we know that this word is probably, have an effect of what comes after. So products like Google Home Assistant or Amazon Alexa, they must be full of these kinds of networks, speech synthesis, translations, these kinds of things. And there are more network architectures that we could look at, but for the scope of this talk, where we only want to analyze images, we are going to focus on convolutional neural networks. That's what we're going to build together. So a little bit deeper in convolutional neural networks, where is their power? Now, to answer this question, I want you to look at this image for 1 second. Now, how long did it take you to tell the rabbit from the cat? Probably nothing, right? It was almost instantaneous. So you looked very briefly at both of them and your brain immediately told you which one was the rabbit and which one was the cat. Now, if you wanted to teach a computer to tell a rabbit from the cat, writing an algorithm, how would you do that? You will agree with me that it would be very, very, very difficult. Like if you try and decompose the process that your brain went through when you saw this image, it would probably be something like, okay, both animals have black and white fur, both animals have 4 legs, and both animals have 2 eyes, but at the same time, one animal has shorter ears, and one animal has a longer tail. One animal has the eyes in the middle of his head, and another animal has the eyes on the side. So your brain did all these calculations very, very briefly and concluded that one is a rabbit and one is a cat. But to write an algorithm that does all this would be very, very, very complicated. And this is where the power of convolutional neural networks come into place. Convolutional neural networks are able, trained with enough images, to understand by themselves what the features are that make a cat a cat. what are the unique features of a rabbit. In this case, a neural network is able to understand it on its own without us teaching it the rules. So this process, if we look at a little bit more in detail, not a lot more in detail, but just the general concept. Let's say you have a use case where you want to train your neural network to tell you whether a rabbit is in the image or not. Now, what you're going to have is you're going to take thousands and thousands of pictures of rabbits. It doesn't matter. There can be different kinds of rabbits, different colors in different settings. And what you're going to do is you're going to label each one of them, saying, here there is a rabbit, but then maybe you're going to have images that don't have rabbits in them. And so you're going to label that image as there is no rabbit here. So you have this, you have built this data set of thousands of images that contains rabbit or not. Right. The training phase of our network is when this network is going to go through all of the images that you pass on to it, and it's going to identify some filters. So the network is going to identify and memorize some filters. And these filters, they will be such that if you look, if the image, is looked at through this filter will tell the network whether there is a rabbit or not. In other words, if you see that image of a rabbit with a grid overimposed on the bottom left part of the slide, during the training phase, the network is going to create such a grid and look at every image through this grid. Now, this grid, you have to imagine it at a pixel level, right? So it's a grid at a pixel level. This grid is going to scan the entire image, and based on the label that you have given to the image, so whether there is a rabbit or not, this grid is going to scan the entire image, and then based on this label, the network is going to change the weights on all the neurons for all the transfer functions of each individual neuron. So we're not going to go any deeper than this, but looking at thousands and thousands of images, for each image and each label associated with it, the weights on the transfer functions of each neurons of each layer are going to be slightly modified, slightly tweaked, all the way until the network going over these images over and over and over again is able to tell the images with rabbits from those without rabbits. This is as detailed as we're gonna go for training, but that's the idea. That's the link between the weights on the functions, on the transfer functions of the neurons, and the ability of a convolutional neural network to recognize objects. This is the important link. All right. Once we have introduced this, we go back 1 second to the multi-layer neural network structure, and we're going to look at a specification for a convolutional neural network. Something like this. If we read it again from left to right, you will have that the input comes from the left, and the first layer is the input layer. Remember, a special layer that propagates information to the first hidden layer. Next to it, there is a convolutional layer. This is the layer that does the work with the grid, scanning the images using this grid that we have just talked about. Next, a subsampling layer. This layer, it's only going to basically reduce the bandwidth. So take the input, the information that comes from the convolutional layer, and sort of half it to reduce the necessary computational power to process it further. So it halves this information and then passes it on to the dense layer. This dense layer is 500 fully connected neurons. In this case, it could be anything. This dense layer, all these neurons are going to elaborate and trigger their transfer functions, activation functions, and then collapse this information down to the output layer, which will finally, in the output, tell us whether there is an object that we're looking for in an image or not. So it will tell us whether there is a rabbit or not, or whether there is a plane or not. Okay, now that we have this very big overview of how convolutional neural networks typically work, we are going to build our own from scratch using Deep Learning 4J, which is Deep Learning 4J is a library to build neural networks on the JVM. So you can use it from Java, from Scala, from all the JVM languages. Just as a word, for my opinion, my experience, I tried using TensorFlow. TensorFlow is another very, very popular deep learning library, sponsored by Google, among others. So I used it, but in fact, I am a JVM guy, and the API in the TensorFlow Java API didn't really feel very Java-esque. It felt like they were, sort of the Python API, but then adapted for Java. So nothing against Python, but if you are familiar with the JVM, probably Deep Learning 4J is a library that will make you feel right at home. So I suggest you give it a try. I recommend it. Now, what we are going to do for our plane case is the following steps. First, we need to take a lot of pictures of the bridge with planes on it or no planes, and we need to label each one of them. So this was a crazy amount of work, actually, that I had to do. It's not fun. At the end of the day, I had to look at all the pictures that my Raspberry Pi took and label them one by one, plane, no plane. Very risky, very error prone. You cannot ask a neural network to do this for you because that's exactly what you want to train. So really pure manual work, very boring, very risk prone. Think twice before starting to to collect your data set. Anyway, these images that the Raspberry Pi outputs, we are going to crop them. So if you see the image on the right, I have just cropped them around the bridge, because in the end, that's what I'm interested in. All the rest in the image is noise. I am only interested in the plane on the bridge. So I'm going to crop the image around the bridge, but I'm also going to reduce its resolution a lot. In this case to, what is it, 171 times 25 pixels. These numbers are entirely random. Maybe there was a reason back then, but also probably not. It just happened like that. But the idea is you reduce your image, you shrink it, because it takes up less space to store it, but it's also faster to read and speeds up training while retaining key information. So if you look at the image on the right, you can see that there is a plane there, even if the image is very, very small. And you know, a neural network doesn't need this crazy amount of resolution and details to detect whether there is a plane or not. So splitting, cropping down images and resizing them is a good idea. So now you have this massive data set, let's say 10,000 images or so. What you need to do is you need to split it in two. This, what you're looking at, is your entire data set. Images with plane, images with no plane. You're going to split this in two. A training set, let's say 80% of the original data set, so in our case, 8,000 images, and a test set, 20%, so 2,000 images. Why is that? Because The training set is the set of images that you're going to use to train your network, to tweak the functions of its neurons. You're going to use the training set, and then after that, you're going to test the network and its performances with the test set, which is, composed by images that your network has never seen before. And so you see how well the training happened, how well the network performs. Once you have done these operations with the data set, it's time to get to some code. For instance, we need to set some initial settings, such as input height, input width, 25 and 171. Depth, that's a very important variable. It describes for each pixel the number of input channels. So in other words, colors. Each pixel is identified by a value of RGB, so red, green, and blue. And so depth in this case will be 3. Other settings like the number of possible outcomes, in our case is 2 possible classes, plain or not plain, and other settings that we are not looking at here. And finally, we are ready to build our network layer by layer. Now, in this example, what you see at the bottom right of this image is, remember, the convolutional neural network architecture that we saw a few slides earlier. And now we're going to build layer by layer this network. On the left side, you are going to see the full network built. All right, it's Java, or, well, in this case, I am using the Java API from Scala, but they look exactly the same. So being Java, we have a builder. Who doesn't love builders? And that's the first thing. Then we're going to add layer by layer, starting with the input layer. You see, we have the set input type, and the input type is convolutional. We know that we'll be building a convolutional network where we specify the height, the width, and the depth of the images that we have set up earlier. Now, moving on to the second layer, it's our convolutional layer. So you see there is a convolutional layer .builder 5.5,5. What is that 5.5? 5,5? Well, that 5,5 is the grid that I mentioned earlier. Remember? The image, during the training phase, each image is going to be scanned by this 5x5 grid that moves along the image, trying to identify features of, in our case, a plane. So the network will learn by itself what are the features that make a plane recognizable. In this case, I don't know, for a plane, it probably will be the presence of this, triangular tail, maybe a sort of a round face on the other side, and maybe some engine kind of wing shape on the side. And the network is going to learn by looking at these images with a 5 pixel by 5 pixel grid. Now, the next layer is the subsampling layer, which, as we said, just halves, slashes it in half, the information received from the previous layer. So kernel size is 2, basically just half, followed by a dense layer, just 500 neurons, boom, all together working fully connected, that are going to do a lot of work for us. And finally, an output layer, which you see an out parameter is num classes, which was 2, plain or no plain. And finally, we build the whole thing. So on the left of the slide, the font is a little small, but you see how we have created this multi-layer network, just layer by layer. It's quite in this sense, there is a correspondence, really quite literally one-to-one between the layer we want to build and the actual code we need for it. A final remark about this code: if you were to copy paste the code from this slide and put it on your, on your IDE, it wouldn't compile, because I simplified this code a little bit. I removed some parameters, but if you want to see the actual working code, at the end, there's going to be a link to the GitHub repository where I put it. So that was it. All right, we have our model, we built it, we deployed it to our Raspberry Pi, and the Raspberry Pi is sitting there looking at planes and making predictions. How does the network that we have built perform over time? Now, when, let's say, the Raspberry Pi sees an image, takes a picture, looks at it, and needs to tell us whether it thinks there is a plane or not on the bridge. All right, if we take this output, this prediction from the network, and we compare it with reality, so once again, human looking at it, we can classify the outcome prediction of the Raspberry Pi into 4 cases. This is called confusion matrix. Starting from the top left, we could have a true positive, where in fact, in our case, there was a plane and the network saw it correctly, true positive, but it could be a false positive just below it. The model tells us, yes, there is a plane, but there wasn't any. Conversely, it could be a false negative, where there was a plane, but the model just didn't see it. Or finally, a true negative. That means there was no plane and the model didn't see one. Now, one word about this is every use case of AI, you will probably have to choose what to favor. It's very difficult to create a network that achieves perfection, that has, always true positives and true negatives. So there's always going to be a compromise between that. And this depends on your use case. For instance, if you're doing, you're in a health sector and you're doing, I don't know, predictions about whether a patient in hospital has cancer. Well, in that case, what you really want to avoid is false negatives. It's much better to scare a patient with a false positive, and then maybe you do another test and more tests, and at the end you see that there was nothing to worry about. It's much better like this than give a patient a false negative, telling the patient, no, you're not sick, while he actually is. So you see, in different cases, you want to achieve different compromises. In our case, how did actually my network perform with my planes? Now, from these 4 categories, you can extract a few measures that are a little more telling. And in this graph, we're looking at 2 of these measures. One is called precision, and one is called recall. The precision is the blue line, and these values fluctuate between 0 and 1. Precision tells us how well the model avoids false positives. What does it mean? As you can see, my network is pretty good with precision. There's many days where the value is 1, the top. What does it mean? It means that during those days, when my model says that there is a plane in the picture, there probably is one. It's very good at avoiding false positives. At the same time, though, the red line, the recall value, the recall property tells us how well our model avoids false negatives. In the case of my network, the recall, oscillates depending on the day, but it's generally quite poor. So that means that my plane doesn't avoid very well false negatives. In other words, it misses quite a lot of planes. in a lot of images that it takes, there are planes that the network does not see. And so this leads me to go back to the images and try and understand what makes the network go wrong. Well, I am based in the Netherlands, which doesn't have the best weather in the world. And so the weather is obviously a major cause of confusion for my network. So see, for instance, in the top left image, it's very foggy. So maybe the network doesn't see the plane very well. In the top right image, it's raining. So the raindrops cover the window. And so the image is very confused. And again, the Raspberry Pi is confused. In the bottom left image, it's pretty funny. Actually, the sun is just in front of the camera. So the contrast is very high and the colors are very dark. Actually, if you squint, there is a plane in that picture, but it's very difficult to see. And then finally, the bottom right image, I think that's very interesting. The network missed that. And then you would say, how is it possible? That's such an obvious picture. Of course, there is a plane on that bridge. Well, but the plane, unfortunately, is incomplete. So for our brain, it's just so easy. It's literally a no-brainer to know that there is a plane on the bridge. But for the network, because it missed the front, well, maybe you remember those filters. Maybe the front is a very important part of the of the process to help the network see the image. And there is one more thing that I want to briefly touch upon, really just 1 minute. Something that really struck me is AI bias. So I live in the Netherlands, close to Amsterdam, and the national air company is called KLM, and its planes are blue. So what it means is that my Raspberry Pi took predominantly images of blue planes. So as a result, when there was a blue plane on the bridge, the network has no doubt. Oh yeah, of course. Sure, that's a plane, of course. But when it saw planes of other colors, say white planes or blue or yellow planes from DHL or red planes, it had a lot more trouble. So if you train a Raspberry Pi in the Amsterdam airport, it will think that all planes are blue. And I don't know, when I realized that, it really struck me like I hit a wall. I really did not expect this. That even a playful project, useless learning project like this is totally vulnerable to AI bias. And so, I made a little research after, and I really think that AI bias is an incredible challenge that humanity has. Creating a data set that is heterogeneous and diverse and representative enough is very difficult. And I'm sure you all remember, some horrible cases, the first experiments like a few years ago of Google and Microsoft that went really badly because of AI bias. And yes, I think that this is a really important topic, and I wanted to mention this. All right, so I am done here. What are the next steps for you? The first step is leave a feedback about this conference. The organizers really appreciate it. I do appreciate it. Feedback is what helps us get better and move forward and grow. So really appreciate it. Then there is a link with the blog post that comes with this talk. And there is a book. That book from O'Reilly, Deep Learning, A Partitioner's Approach, is the main source of my deep learning knowledge. I would totally recommend it. It's not very new. It's from 2017, but these concepts haven't changed much at all in the last few years. And then finally, the recommendation is if you are inspired by this talk and you want to experiment a little bit with it, I suggest to find a fun use case like my planes, and a data set in a domain that you know. Maybe something at your job, something that you work with. Maybe you are a tree. I don't know. Maybe you're a botanical expert. So maybe you can experiment with plants images or something like that. If you want as a reference, at the bottom there is a link to my GitHub repository where all the code and actually the data set is also there of my planes images. And this is it for me. Thank you very much for your attention, and thanks to the organizers for organizing this conference and having me. I am going to stop my video sharing.
Yeah, it went well, and we did answer most of it. I'm just seeing if there were any other live archives yet, or yeah, room 2, I don't see anything more. Slack channels all done. Cool. Awesome job, Fabio. Thank you so much.
Thank you for having me.
Thanks.
Bye.
Bye.